This video is about using stoichiometry to calculate limiting reactants and leftovers. So far we've assumed that there's enough of each reactant to make the product that we want. The limiting reactant is the one that runs out first, and it determines how much stuff you can make because it's gone. So the example we're going to look at is an ice cream example. So we're going to make sundaes, and every sundae requires 2 scoops of ice cream to 1 cherry to 50 milliliters of syrup, and that gives 1 sundae. So we're going to figure out how many sundaes we can make with a certain amount of stuff and what's going to be left over. So here's the stuff that we are given to start with. We've got 8 scoops of ice cream, 6 cherries, and 100 milliliters of syrup. So one of the things that we can do is to go through each reactant and figure out how much we can make from that. So with this much ice cream, we could make 4 sundaes. With this many cherries, we could make 6 sundaes. With this much syrup, we can make 2 sundaes, which means we can only make 2 sundaes, because at that point we are going to run out of syrup and there's no more syrup, and it doesn't matter how much of everything else we have. We will have 4 scoops and 4 cherries left over after we make the 2 sundaes. So let's say we have 50 scoops of ice cream, 30 cherries, and 1 liter of syrup. So again, go through each amount and figure out how many sundaes you could make. And we could make 25 sundaes from our ice cream, 30 sundaes from the cherries that we have, but only 20 sundaes from 1 liter of syrup. So this will give us the smallest number. So it is limiting and it will run out first. We cannot make 25, we can only make 20 because the syrup, which is limiting, is going to run out. So here we have a reaction, chemical reaction, particle diagram. We've got B2, B is the reds, so these little red guys are B2, plus AB, blue is, A is blue, and they react to form AB2, which are these guys here. So there's a typo here. I want you to fix that. So here's our balanced equation. We've got B2 reacts with AB to make AB2. To balance it, needs a 2 here and a 2 here. So that's why it's so important to balance the equation, because it's going to give us the ratio of the reactants and the ratio of the reactants and the products. So figure out which one is going to run out first. AB runs out first because it's going to keep going until something runs out. And in this case, for every 1 B2, we're going to need 2 of these guys, and that's going to give us 2 product molecules. So that actually happens twice, and AB runs out, so it's limiting. And I still have a B2 left over. See, this one left over here. So then we're going to combine this with moles and do some, mole calculation. Here we've got a balanced equation. Chlorine trifluoride gas is formed, so it's the product from chlorine and fluorine gases, Cl2 and F2, which are both diatomic. So there's our balanced equation. We need the 3 at the fluorine and the 2 here. Starting with 5 moles of F2 and 5 moles of Cl2, how many moles of product can be made? So what we're going to do is look at both reactants separately and figure out how much product we could make from each one. So from our fluorine, 5 moles of fluorine, again we use the mole ratio 2 to 3, we could make 3.3 moles of product. But from chlorine, 5 moles, with its mole ratio, we could make 10 moles of product. The one that matters is the smaller one, because when we make 3.3 moles of product, it means that the fluorine is gone. It's just like the syrup in our example. Once the fluorine's gone, we can't make any more. So 3.3 is the most we can possibly make. That's our theoretical yield. The 10 here doesn't actually mean anything. It's kind of it's a number that tells you that the 3.3 is the right number. So F is limiting, it runs out first. And what's going to be left over? So we're going to do a little bit more math here. We have to figure out how many moles of chlorine get used when we make our theoretical yield of 3.3 moles of product. So that's our given, 3.3 moles of product. We know we're going to use 1 mole of chlorine for every 2 moles of product. So we are going to use 1.65 moles of chlorine. We start with 5. We subtract out how much gets used, 1.65 minus 1.65. And this is the amount of chlorine left over. So the way that we're going to do stoichiometry problems, like full stoichiometry problems, is we are going to use something called an ICE table. So we're going to set up an equation, balance it, calculate the molar masses. But here, instead of just giving one given, we're given 2. So we mix 50 grams of sodium sulfate with 50 grams of carbon. What mass of sodium sulfide is produced? So we need to see which one is limiting and which one's going to give us a theoretical yield. The other one's going to be left over, and we have to be able to calculate that. What an ICE table is, it's a table that describes in moles the initial, the change, and the ending, and all the numbers in it are mole units here. So let's start to set this up. First thing to do is balance your equation if it's not already balanced and calculate the molar masses like we normally would for any stoichiometry problem. The next thing is for both of the reactants, convert grams to moles. So for both 50 grams of sodium sulfate and 50 grams of carbon, for each of them separately, calculate, convert those to moles using the molar masses. And then we're going to set up an ICE table. So what an ICE table is this sort of grid table. Across the top, we write out the reaction, space it out a little bit to give ourselves some room, and then along the left-hand side, we write the letters I, C, and E, and separate them out so you can makes it easier to keep organized. I is the initial moles, C is the change in moles, and E is the ending moles. So the next thing we're going to do is calculate the moles of both of our reactants. Same old way, take your grams, divide by molar mass, convert to moles. These numbers here are going to go in our ICE table under initial because it's how many moles we started with. And because we haven't formed any product yet, the product moles always start out as 0. So then the next thing we do, so we put in the numbers, the starting moles. Then looking at our balanced equation, we look at the coefficients. So we are going to lose, the ratio that we are going to use is for every 1 sodium sulfate, so that gets a minus X because it's going to be getting used up. We are going to use up 4 carbons, so that's a minus 4X. We are going to be forming 1 sodium sulfide, so that's a plus X. And then we're going to form 4 carbon monoxides, so that's a plus 4X. So the minuses are with the reactants, and the pluses are with the products, and then the number is the coefficient for each one. And X is just the factor that we measure everything by. So the next step is to solve for X. And the way that we do that is this. We are going to solve for X for both reactants. So we assume that both reactants are going to all get used up. So for sodium sulfate, we start with 0.352 moles, and the minus X here is from the minus 1X here. and we set that equal to 0. So it's 0.352 minus x equals 0, and then we solve for x. And then we do the same thing for carbon. So the starting moles are 4.16. That comes from here, 4.16. And then for carbon, it's minus 4x, and that's because it's minus 4x here, and that's because of the 4 in front of the carbon here. So 4.16 minus 4x, set that equal to 0, solve for x, and x is 1.04. The only one that matters, again, is the smaller one. This is x, 0.352. So now that we have our factor, we have our x factor, we have the smaller, it's the smaller number, that's going to be the x. That's always going to be from the limiting reactant, so we know that sodium sulfate is going to run out first because it gave us less product. So we take that x and we plug in the math here. So we're going to do 0.352 minus x, and what do we have left? And we're going to do that for each reactant. Sometimes I don't give myself enough room here, so try to do a better job than I did. So let me explain what's going on here. So the change is going to be the starting moles minus the number of x's. And this is going to be 0 because sodium sulfate is our limiting reactant, which means it has to have nothing left over. So carbon is not limiting. We're going to have some carbon left over. So the change is going to be the moles that we started, which is 4.16, minus 4 times x, so 4 times 0.352. Plug this into our calculator, and we get 2.75. So this is the moles of carbon that's left over. And then we can figure out how much product we made for both products. So sodium sulfide plus x means it's just going to be 0.352 because it's just 1x, coefficient of 1. And for carbon monoxide, because of the 4, it's going to be 4 times x, which is 1.408. So these two numbers are the moles of product that we are making. 0.352 moles of sodium sulfide and 1.408 moles of carbon monoxide. The question in our problem was, what is the mass of sodium sulfide produced? So that's the one that we care about. If we'd been asked about carbon monoxide, we would do the other one. But the mass of sodium sulfide produced is the number of moles from our ice table at the bottom, change it back to grams, multiply by its molar mass, and that gives us grams. The mass of carbon left over, remember at the end, this is how many moles of carbon are left over. So it's 2.75 moles, multiply by molar mass to get the grams of carbon left over. So this is the grams of product, and this is the grams of carbon leftovers. Okay, so on the next page, I'm going to try another one, and stop your video and set the whole thing up. Check and make sure your equation's balanced first. Go through and write the molar masses because you're going to need those. Calculate the moles of both starting materials, 100 grams and 100 grams. And then set up your ice table and then use that to calculate all the moles of everything at the end of your reaction, and then convert stuff back to grams. Use the other one as a model if you get stuck, and then turn your video back on and check and see how you did. Okay, so the first two steps, calculate molar mass, and then for both reactants, convert from grams to moles. Okay, so then setting up your ice table, write the reaction across the top, and then under each column you'll put the moles of each formula. ICE down the left-hand side, initial, change, and ending, and then the number of moles across the top. So we start with always 0 moles of product, and then the moles of the reactants that we calculated over here. So then we set up the x's, and the reactants are always minus, and this has a coefficient of 1, so it's minus x. This has a 3, so it's minus 3x, plus 1x, plus 3x, and plus 1x for NH3. So then using the numbers over here, we're going to solve for x for both of them, assuming that they all get used up, and see which one is going to give us a smaller x. So do 2 separate calculations to solve for x. For sodium nitrate, it's going to be 1.17 minus x, set that equal to 0. X is 1.17. For sodium NH2, 2.56 minus 3x, set that equal to 0, and x is 0.85. So this one gives us the smaller x, so this is x, and this is limiting. So then do the change calculations. Again, it can be hard to fit them in. So x is 0.85, and we use that as a factor to calculate what's left at the end. Since sodium nitrate is not used up, we are going to have leftovers. So 1.17 minus 1x gives us 0.32 left over. Sodium amide all gets used up, so this is how we figured out x. There's going to be 0 left over. 0.85 moles formed of NaN3, 3 times x, or 2.55 moles of sodium hydroxide, and 1 times x, or 0.85 moles of NH3. So then we look at what we need to calculate at the end. Go back and read the question. It says, what mass of NaN3 is produced? And I think I calculated the wrong one here. Nope. It's fine. So we look at sodium N3, and it's 0.85 moles, which comes from this number right here. Convert it back to grams, multiply by 65.01, 55 grams of NaN3 produced. How much sodium nitrate is left over? This is the number of moles left over, the end of our ice table. So that's going to be 0.32 moles times 84.99 grams per mole. It's 27.20 grams left over of leftover sodium nitrate. Okay, so now you guys know how to do ice tables. They take a little while to get used to, and we'll be practicing them more in class.